Good afternoon, everyone. Hopefully you can see the opening slide there, Monitoring Evaluation Solutions. I'm Luke Smith from Build Test Solutions. And here to talk on the subject of all things measurement, monitoring, evaluation, and to put it into context for you. So agenda-wise, I thought we'd cover the topic of what is building performance measurement, and what does that mean when we're thinking about particularly sort of managed housing stock portfolios. We want to look at then why is it important, why measure. We'll then cover sort of some of the available tools and techniques that exist. Build Test Solutions are a supplier of some of those tools, but I can certainly shed some light on others that are available as well. And then we'll look at some case studies, so examples of where measurement has been applied to good effect and to the benefit of numerous stakeholders on retrofit projects. And then we'll wrap up, and like Louise says, we'll try and reserve kind of 15-20 minutes at the end to have a bit of a more open discussion. Just before we get into what is building performance evaluation, this is the one slide I've got about me and Build Test Solutions. So my background, I trained as an architectural technologist. The early parts of my career, I was working directly on behalf of social housing providers on various retrofit projects and programs. I was involved in, going back some way now, but the Retrofit for the Future program, the Innovate UK Building Performance Evaluation program. And an area of interest for me was always this topic of measuring and validating building performance. So how do you measure and check that a building performs in line with design expectations or the assumptions that you might otherwise be working with? And what I generally found was that there was, whilst it was always a really interesting area, it was largely a field led by academia. So where housing associations, this is going back kind of 10 years or so, where housing associations were carrying out monitoring and evaluation and measurement, it was typically university led, and it would be, I wouldn't be exaggerating to say, in the order of 10, 15, 20,000 pounds invested in a single property to forensically measure and evaluate how it performs. And that's all really interesting, but clearly not at all scalable. And so it was driving interesting reports and PhDs and all of that kind of thing, but really measurement tools and techniques, I think, haven't traditionally been all that accessible. It's been deemed as quite a technical topic, quite a difficult, disruptive, invasive thing to do in people's homes. And so we formed Build Test Solutions in 2016, and it's all about kind of bridging this valley of death. So we work closely with lots of those universities, the likes of University of Salford, Leeds Beckett, Loughborough, UCL, and many others, and work with them to develop novel approaches to measuring building performance, and then trying to develop those methods, turn them into products that can be used by the mainstream market. So tools and techniques that can be adopted by the existing retrofit assessor community, existing energy assessors, building surveyors, so that measurement needn't be a highly specialist, expensive activity. It can be something that we can more widely practice on buildings at large. So that's what we're all about with Build Test Solutions: discovering, developing, pulling through innovative measurement tools and techniques for the market to adopt at large. It's not our domain to be out there offering measurement as a service. That's more for our customers, which is why I sort of think it's worth setting out that context early on. Okay, so then when we think about what is building performance measurement, I think it's worth starting with the headline matter of actually what are we trying to achieve from our retrofit projects. I don't think there's anything contentious here at all. I think you'll all largely agree that retrofit's a good thing, seeking to improve the energy efficiency of homes, reduce the carbon footprint, make them more affordable, to run healthier living environments. We're all out to address and mitigate fuel poverty, of course. None of us want to see overheating in homes. There's a degree of there's a natural order of updating and upgrading. So obviously lots of components of buildings have a given service life. And so there's invariably a degree of, boilers are up for replacement anyway. Let's look at heat pumps as a more efficient alternative. Windows roofs, they will have a given service life and up for replacement anyway. And then there's compliance, of course. There's things like building regulations and other voluntary standards and self-imposed goals that are driving retrofit activity in the marketplace. But then I think it's a real challenge to determine how do we best measure and verify those delivery efforts. So how do we know that we truly are addressing fuel poverty? How do we know that we truly have, through the retrofit activities, reduced the CO2 emissions of the homes? And so tools and techniques or methods that are commonly employed that you'll be familiar with, see stock condition surveys, a widely practiced activity in the sector, predominantly been sample based and orientated around trying to determine the remaining service life of components. So condition based review and replace kind of cycle. We've got energy performance certificates that we all know and love. I think it's fair to say there's lots of housing associations out there that are very much have sustainability strategies, retrofit strategies that are led by EPC ratings. For instance, we want all of our stock to be an EPC band C or above by 2030 or whatever given date it may be. And some of you may be closely looking at smart metering, and energy companies have commitments to roll out smart meters across the building stock. And so there's an opportunity there to piggyback that, and you've got the digitization of energy data. And so then it is possible to remotely see how much properties are consuming at the meter, what tariff those residents are on, what's the associated cost for those residents operating those homes. And then many of you will be familiar with the bit of a sort of boom that we've had in recent times of IoT monitoring, IoT sensors. So Internet of Things, temperature, humidity, CO2 sensors, gateways that can be placed in people's homes and allow us to remotely see the environmental conditions of a property, potentially get eyes on the smart metering and help pull it all together into a dashboard for us. But again, I would encourage we stop and think at this point as to what are the key metrics, thinking back to the previous slide, what's actually driving our retrofit programs, and do we have an asset data strategy that really pulls all this together and makes it clear as to what aspects of the buildings and their performance are we trying to track and why. And just this image on the right hand side of the slide here, just trying to portray that clearly we're dealing with quite a complex environment. We've got the physical building and the fabric and the envelope of that property. We've got the systems that serve that property in terms of the heating system, the ventilation system, and of course then the people, the residents living in those homes, all of which operating within a changeable environment. The wind, the rain, the sun, summers and winters that are having an influence on these things. And so it makes kind of tracking progress on retrofit projects even more difficult, where obviously we've got people with different energy use behaviours, different cultures, different cooking habits, different levels of occupancy influencing the energy consumption at the end meter. We've got the energy heating systems, hot water systems, ventilation systems that again are influenced by occupancy factors, but also influenced by the performance of the fabric itself. So there's lots at play that make, again, this idealistic idea of being outcomes-based, outcomes-orientated, quite challenging. So from where I'm coming from, where we encourage a lot of focus is around measuring and understanding the building fabric in particular. So the message here from me is control the controllables. So you can absolutely deliver behavior change programs, you can absolutely monitor environmental conditions and make sure that people aren't underheating, overheating homes. But really a lot of that's outside of your control as a housing association. Whereas the building fabric, the physical asset, the walls, the floors, the windows, the roof, that is absolutely in your gift to upgrade and improve. And so when we talk about building performance evaluation, I'm thinking very much in terms of methods of measuring and evaluating the fabric performance as a first port of call. So By this, we're thinking about whole building heat loss measurements, so otherwise known as measuring the heat transfer coefficient of a building, or HTC. We could be measuring the air tightness, the enclosure integrity of a building fabric, pulse and blower door test methods. We could be measuring the U values of specific elements, so what's the heat loss rate through the given floor structure, through the walls, through the roof. We could be measuring ventilation flow rates. So yeah, how, if that's infiltration, how leaky is the building, but also what's the rate of air changes being delivered by mechanical ventilation systems installed. And yeah, from some of that, you can also start to determine mold and overheating risk from some of these environmental condition sensors, temperature and relative humidity sensors, which we'll come back onto in a moment. So I would surmise what is building performance measurement as something that's carried out on site, physical measurements at a given point in time, typically measuring things like the heat loss rate, the air tightness, U values. And yeah, there's all sorts of terms bandied around, but yeah, could otherwise be known as the building performance evaluation. Post-occupancy evaluation is another term commonly used. Monitoring and evaluation, as per the title of the presentation, M&E. Monitoring and verification, M&V. But yeah, we would categorize that activity is very much kind of measuring aspects, particularly of the building fabric performance on site at a given point in time. And we encourage this approach because things like a heat transfer coefficient or the air tightness or ventilation flow rates, U values, are absolutely smart metrics in terms of they're specific, measurable, achievable, relevant, and can be time bound, i.e. measured at a given point in time. It's really difficult in a property to measure energy use and whilst also factoring in occupancy factors. It's really difficult to measure the CO2 emissions, taking into account heating system efficiency and disaggregating heating and hot water and that kind of thing. Lots of fluctuation around fuel costs and the emission factors associated with fuels. But actually, by delivering a building that has a very low heat transfer coefficient, very low heat loss, good thermal efficiency, good levels of air tightness, adequate ventilation, you're by proxy delivering something that will invariably have lower costs to run, lower emissions, lower energy use. Then, yeah, I'm not blind to the fact that, of course, measurements on their own, like sort of measuring things like HTC, air tightness, U values, flow rates, is the be all and end all. I think it's important to recognise where these sit in terms of a wider framework. So we'll all be very familiar with modelling activities. So producing RDSAP, full SAP, EPCs, planning house package models and simulations of buildings, the incoming home energy model, other dynamic simulation tools. And these are very helpful tools to allow us to assess a building and project what impact measures might have. But in isolation, a building model is extremely vulnerable to this kind of idea of garbage in, garbage out, basically. So if you're feeding your models with unknowns around the thermal performance of the building, we're speculating as to what insulation might be in the walls and therefore what the baseline U values of a wall structure might be. We're speculating as to the level of thermal bridging. We're doing the best we can with modeling of thermal bridging, but actually it's still just a model and a prediction. And so all of these assumptions stand to compound and present quite high levels of uncertainty overall in kind of the modelling of our buildings. So I think, yeah, modelling in isolation has its risks. And so when I talk about measuring these particular sort of fabric performance characteristics, that's with a view that then those measurements can in turn be plugged into your models to reduce the uncertainty and improve the precision of the modelling. And then we've also got the supplementary activity of what I would term monitoring, which is rather than a point in time measurement of a building performance characteristic, we're talking about, again, going back to those IoT sensors, monitoring the environmental conditions in a home over time. Again, I wouldn't advocate that type of monitoring wholly in isolation because, of course, temperature in people's homes is going to fluctuate all over the place. Relative humidity levels are going to fluctuate. Yes, of course, you don't want people to be in extreme cold conditions or overheating or very high relative humidity conditions and then therefore being exposed to mold and condensation risks. But we've got to recognize that all those environmental conditions are heavily influenced by the weather, the occupancy effects, and occupancy behaviors. And so I think what I'm trying to say with this is that no one of these three things should stand in isolation. Measurements shall stand to inform your modeling activity, and then monitoring is almost your safety net. Sort of post retrofit, let's just keep eyes on assets and know that they're behaving in line with expectation over a longer period of time. And of course, that can then trigger your tenant support activities around call outs and verifying that if a tenant does have an issue with heating their home, you can see that in the data as well. So yeah, just to really drive at that idea of modeling and measurement working in harmony. So many of you will be familiar with SAP worksheets that are used for generating an EPC. So all that's going on within that modeling software is we're taking each element in turn. So in this case, we've got the windows, the doors, the ground floor, external walls, roofs. We're measuring the area that those elements present. And then, like I touched on before, we're assuming the U values or projecting what we think the U values are likely to be based on the age and predominant construction type of that element. And then that's giving us a heat loss rate per element. That is all summed up to give us a total fabric heat loss rate. We're adding in some thermal bridging, line 36 there, to then ultimately arrive at this line at the bottom, a heat transfer coefficient. And so when I refer to measuring a heat transfer coefficient, you can measure that number directly in situ within a building. And from that, you've essentially bypassed all of these assumptions around thermal bridging and assuming U values for each individual element. Thermal bridging is something that's really difficult to otherwise model or calculate. And so by sort of jumping straight in and measuring the headline HTC, you've bypassed all the risks around assumptions here, or at least been able to then help calibrate, sort of backwards calibrate your model. And then thinking back to, well, actually your drivers as an organization are around reducing energy demand or improving the EPC rating. Just a couple of charts here to show that an improvement in HTC has a direct linear relationship with the space heating demand and the SAP rating. So naturally, if you reduce the heat transfer coefficient of a building, make it more thermally efficient, then you are by proxy reducing the space heat demand, of course. Similarly, if you're reducing the HTC, you're improving the EPC rating in a linear fashion. So I do totally appreciate that something like a heat transfer coefficient or measuring U values can feel quite abstract, but it's something that's absolutely measurable and can be directly influences the things that we are ultimately interested in terms of outcomes. So moving on now, just to think about why measure, and this is again kind of really driving at the HTC thing in particular. So here we've got a 1950s, that's slightly earlier than actually 1940s or so, post-war estate, southeast London. Visually, the semi-detached properties are all very similar. And with RDSAP, sort of on an EPC, they all present as the same rating and all very similar performance. But actually, when we've been to these homes and measured the heat transfer coefficient, we've seen quite a spread of performance. So on one hand here, we've got this is 10 properties in total, by the way. This one bar is representing a single property that's got 43% higher heat loss than the EPC model had us believe. And this is purely comparing predicted heat transfer coefficient. So that extra heat loss is nothing to do with occupancy or any other variables like that. It's just how well the fabric performance has been modeled by the software. So in this case, this resident actually has much higher heat loss through their building fabric than this SAP model had us believe. But then conversely, this one had 37% less. And so even though visually they're very similar, and quite interestingly, on average, the EPC modelling is within 1% overall, you've got these quite significant variations. And that's down to the fact that, yes, they may well all have double glazing, but some of those glazing units will have deteriorated or not stood the test of time quite as well as others. Or loft insulation may well be installed, but yeah, how well is it installed? Are there means of heat able to sort of bypass that insulation? And so some of that is really difficult to pick up on in a visual based inspection, like an EPC survey. Whereas a measurement of HTC is really able to pick up all of those nuances, the fact that, yeah, no two properties are ever the same. And here's the same sort of thing, but not this time a low-rise block of flats in central London. And again, here you can see that whilst on average the EPC productions aren't terrible, sort of within 14%, you've got some much higher heat loss than the model would have you believe, and others that are much less. And I think actually in this particular case, the discrepant that those differences were driven by, if I get this correct, the top floor flats had much higher heat loss than anticipated, simply because a visual survey isn't able to know with confidence as to how much roof insulation there was. So without core drilling and taking the roof structure apart, this flat roof, you don't know how much insulation is in it. And I think the much lower heat loss properties were the mid-floor ones that were benefiting from heating above and below. And so this kind of thing, where this is measuring a sample of 20 homes within the block, can really help inform your retrofit investment decision making. So yeah, actually some properties much more thermally efficient than others, and therefore it's going to, yeah, it might dictate kind of what level of insulation you might install and what kind of aspects of the fabric you might prioritize, for instance, the flat roof in this case. Okay, and then scaling that one step further, this is a study we carried out on behalf of DESNZ and in partnership with the Energy Saving Trust. This was again to look at how well the SAP model predicts heat loss, the thermal performance of buildings. And so across a sample of 500 homes, we had measured heat loss and compared that to SAP predicted heat loss. And you can see that the predictions are good on average. So there's this quite clear sort of this dotted blue line is the trend line through the points. If measurements and predictions were to agree perfectly, they would follow this black X equals Y line. And so the trend line broadly follows that. And so on average, as a policy tool, the RDSAP and EPCs work quite well. But actually, the points on the line only represent 42% of cases. And you can see there's lots of dots well above and well below the line. And so differences from the model of 50% or more are pretty common. And so that's again, it's emphasizing this point that, yeah, to paint a broad brush picture of the stock, EPCs and kind of SAP style data is okay. But when it comes to an estate level or a street level retrofit project, the tools that we use, modeling that we use, the assumptions that we know and love are quite blunt and don't particularly do a good job of representing the uniqueness of every individual home. And I think that does stand to influence, again, kind of what retrofit strategy you might adopt. So that's me really driving at HTC's measured heat loss, whole building heat loss rate in particular. But then we also see that in air tightness tests. So here's a sample of 13,000 pulse air tightness tests. You can see there a nice bell curve distribution. Currently, if you're running a model of a home in RDSAP, the air tightness is assumed to be in the region of 10 to 15 meters cubed per hour per meter squared at 50 pascals. And so that's landing all properties, deeming all properties to have an air leakage in this sort of area. So let me move my pointer. So yeah, in this sort of range. And yet from these 13,000 tests, all of which are on existing homes, the mean air permeability is closer to 8.7 at 50 pascals or 1.7 at 4 pascals. So again, our models are quite conservative and assuming the situation to be worse than it often is. So more often than not, if you turn up and measure the air tightness of a home, it will be more airtight than you might have expected. And to some extent here, you've got properties that in this range here, properties that are more airtight than than modern day new builds. So this is commonly kind of 1950 sort of high-rise blocks of flats and things that are concrete slab floors, concrete intermediate floors, well file compartmentalized, wet plaster walls, double glazed, all the service risers well sealed. And actually you're dealing with properties that are really quite airtight. And obviously the ventilation strategy for those needs to be tailored accordingly. So again, hopefully you're seeing a bit of a sort of trend in what I'm trying to say here is that no two properties are the same. There's quite wide sort of variations in how properties perform compared to what models might otherwise have us believe. And then same again here for U values. So this is actually a study carried out by the BRE across 300 homes. We assume solid brick walls to have this is only the difference actually, but I think this is in the order of 1.7, 1.8 U value. But you can see again, you've got this distribution of properties on this side where the heat loss rate through the walls are much less, and properties this side, walls this side, where the heat loss is much greater. And so whilst the mean may well be 1.7, 1.8, you've got a range here of it could be but plus minus 2.6 from that almost, or minus 0.6 from that, or plus out to plus 2 on it. So again, it's a dangerous game to assume the law of averages and that every property aligns with these assumptions that we often make. So yeah, we can improve business as usual by replacing assumptions with measurements. We can either measure U values, we can measure airtightness, or we can measure HTCs and plug those straight into the models. So I'm not saying we should be throwing that in the bin or using another platform, some modeling software. It's more about any modeling software is going to be sort of could stand to fall victim of the quality of and accuracy of the inputs put into it. And once you have an accurate model, accurate understanding of the building fabric, everything else flows much more readily from there. You now, by knowing the fabric, you now know the peak heat demand that a heating system needs to meet. So then you can size heating systems more reliably, particularly important when you think of heat pumps and the fact that they need to be in the ideal operating window to be most efficient. It's going to inform your ventilation strategies, so how airtight is the building and therefore what ventilation system is going to be most appropriate. And with a good, robust model and understanding of the building fabric, you can then model behavioral aspects with more confidence because the fabric is a known quantity. The building services, particularly gas boilers and things, are quite consistent in their efficiency, and so then you can move on to modelling occupancy as well in a more confident manner. And so unexpected performance delivers unintended consequences. So what we're forever kind of hammering home is you can't manage what you don't measure. And so this is enabling better targeting, prioritizing of retrofit activities. It's informing retrofit design and specifications. By having a before and after measurement, you can use it for quality checking and verification. So I don't think we're far away from a world whereby measured performance forms part of procurement contracts and things. So hold contractors to account based on the delivered performance, not just the theoretical before and after EPC rating or the modeled before and after EPC rating that can be manipulated to suit what was originally sought. So measurement can be a very objective, robust way of checking and verifying outcomes. And then of course, by measuring, you're improving feedback loops and informing future projects about what works well and not so well. And so then you may ask the question, well, why doesn't everyone measure? And this comes back to my earlier point in the opening slide, really, is that traditionally measurement's been deemed as quite an academic undertaking, quite expensive, quite onerous, quite disruptive, and some just completely shy away from it because it's deemed as Pandora's box, and actually we'll just continue with the status quo and trust our models. But we're really trying to challenge that here at BTS. We're developing new tools and techniques all the time, and like I said earlier, with a view to making measurement much more accessible and affordable for mainstream adoption. I place this slide in here as well, I think it's important that we also acknowledge that we're measuring for the right reasons. So the last thing we'd want to see is that we make a shift away from some of the assumptions that we're plugging into models only to perhaps seek to manipulate measurements on site. And so this is an excerpt from a paper that UCL produced a few years back that looked at airtightness compliance tests used in new build. And so here you can see a very artificial looking distribution, shall we say. So looking at this top one here, this is the sample of data whereby the target airtightness of a given new build was 3 meters cubed per hour, meter squared at 50 pascals. And lo and behold, lots of the data achieves 3 or better and drops off a cliff. Similarly, you've got target of 4 and nothing any worse than that. Target of 5, nothing any worse. Target of 6, nothing any worse. And so, yeah, that's also not the point what we're advocating here. It's about measuring, appreciating the nuance of every building, and then developing retrofit strategies developing strategies accordingly. But just to elaborate a bit more on some of the available tools. So yeah, we've talked a lot about whole building heat loss, measuring HTCs, and measuring airtightness with both pulse and blower door technique. We've got techniques around measuring U values. So the academic incumbent method here is the heat flux plates. Something we've been involved in developing is a method called Heat 3D, and we can measure ventilation flow rates. We can measure and evaluate mold and overheating risk by using temperature and relative humidity sensors. There is also a lot to be said for carrying out occupants surveys, so garnering the views of the occupants. They're often a good sensor in their own right in terms of where is the building most comfortable and usable, and vice versa. And thermography is a useful tool, but we should acknowledge that it's purely qualitative. So again, thinking about smart metrics, you wouldn't just do thermal imaging before and after, because you don't. Yeah, how do you compare those images? How do you know the conditions for each set of images? How do you compare and know that your retrofits? Yes, you can check that your retrofit's working, the insulations haven't got any thermal bypass and cold spots. But again, it's not quantitative in terms of defining the impact that you've delivered. So the way we generally talk about these tools and techniques is a bit of a triage approach. So we would first advocate that high level, we want to understand the building stock and use that as a basis for prioritization. So we can measure GCs at large very cost effectively. Again, you can do quite large outreach programs and do occupancy surveys quite readily at large. And then based on what those measured HTCs are telling you in relation to perhaps existing data you may have on EPCs, you can then start to drill down and say, okay, for particular properties with very high measured heat loss, let's try and understand why those properties have such heat loss. So let's measure the airtightness and understand what proportion of the heat loss is attributable to air leakage. Let's understand the ventilation performance and understand mold and overheating risk in those particularly high heat loss homes. And then from there, at your discretion really, but you can drill down further if you did want to specifically understand heat loss rate through the walls, the floors, the roofs with U value measurement and perhaps some thermography. So definitely not advocating throw the kitchen sink at it, do measurements on every single property to the nth degree. It's more, do HTCs at large, which can be done with smart meter data, low cost sensors, and then drill down from there, basically. I was cautioned about using this slide. It's not a sales pitch. This is some of what Build Test Solutions are behind. So we've got the pulse air test method. The other alternative there would be the blower door fan, so a doorway mounted fan instead of this compressed air based system. Similar to a blower door fan, we've got this leak checker device, which can be window mounted to depressurize a building and help particularly site teams when on site find and address air leakage points and check draft stripping effectiveness and things. We've got smart HTC, which is our method of measuring the HTC of a building. And so, like I said, this can be done very cost effectively with some low cost temperature loggers or through integration with existing IoT sensors in a home, and either by manual meter reads or through smart meter data. Very much something that a retrofit assessor or an energy assessor can deliver quite cost effectively. And then this one on the bottom right is Heat 3D. So this is our thermography based technique for measuring U values. The alternative there would be heat flux plates. But the innovation around Heat 3D is that this tripod can be set up and a measurement run of the in situ U values within the space of an hour, whereas heat flux plates, you would typically need to leave those within the property for a minimum of 3 days, typically a week. So again, it's just that little bit more disruptive for an occupant to leave sensors in their home, sellotape to the wall and things. Okay, mindful of time, just finally then some case studies. We mentioned this one earlier. So this is the low-rise block of flats in central London. We learned that, the performance gap was, performance of the top floor was being influenced by the roof insulation. Maybe I got the example wrong earlier, actually. So the mid-floor flats were where they were suffering from higher heat loss. And this was down to this exposed balcony having higher heat loss through it. So you see these rooms encroach above this sheltered balcony. And that's what SAP didn't do a very good job of modelling was those exposed areas. And so then, like we touched on, that enables much better targeted informed retrofit design. You would actually just insulate those balconies rather than necessarily having to put a full wrap around the whole building. This is another interesting one. So this is a private householder in Bristol, quite an engaged individual, already had run lots of models, simulations of the thermal performance of their home. And they were having a ground source heat pump installed. And actually, when they measured the heat loss of the property, it was much more thermally efficient than the model suggested, which led to, this is a one-off single isolated property, it led to needing one fewer borehole. And so then quite a significant capital cost saving. And then the system is ultimately sized more correctly, better, so it operates more efficiently throughout the system's lifetime. And so, you've, again, making much more informed decisions with the measurement. And then some of you will be familiar with the Installation Assurance Authority Trustmark process of background ventilation testing. Clearly, ventilation is really important in our buildings for healthy internal environments. And so, this small bungalow whole building was measured for air tightness, but then individual rooms to find actually that there was one, I think in this case, one particular bedroom where the door was rubbing on the carpet, and that room was particularly airtight. Otherwise, the intermittent extract and the trickle vent strategy was probably adequate for the given levels of leakiness. And so you're doing a much more kind of informed, targeted approach of, well, we know we need for that particular bedroom, improve the door undercut, add a passive vent in that one particular room. So informing ventilation strategy through measurement and testing. And then here we have measuring of U values. So this is in Norfolk, so really nice looking granite stone wall. You would never core drill that, or an energy assessor stands no chance of reliably sort of calculating what the U value would be. Yes, you can use your tape and measure the thickness of the wall, but RDSAP would have assumed the U value to be 2.2. It's measured at 1.2, so half the heat loss of what was otherwise assumed. So this is a Heat 3D thermal image time-lapse survey that was run on this particular property. So again, that's a high conservation value property building. You would never externally insulate that. It'd be challenging to internally insulate it. By measuring the U values, you've actually determined, well, actually the investment case for insulation isn't there anyway. So you'd focus your spend elsewhere. So in summary, we must remain resolutely focused on the real world impacts of the efforts we're going to retrofit our stock. It's really tempting to just be led by predictions and models that perhaps present themselves as fairly convincing, but really when you get to an individual, a street or estate or property level, then every home is unique, and we need to recognise that fact. And so things aren't always what they seem, and we shouldn't target our spend based on poor data and assumptions about assets, which hopefully is a given. And so in situ measurements are a natural extension to existing surveying and assessments. And whilst I'll be the first to admit there's going to be additional upfront cost in obtaining some of these measurements, it's going to involve an assessor being in the property that little bit longer than doing a conventional energy assessment or retrofit assessment. The benefit longer term in terms of informing the retrofit design, the specification, the value of then being able to go back after the retrofit and measure and use that as for quality assurance purposes, and potentially leverage finance and carbon credits because you've measured directly the impact that your spend has had. I think that is the direction of travel for the industry at large. And so control the controllables, particularly sort of focus on understanding the fabric performance of your assets, and then kind of the ongoing condition monitoring is kind of secondary to that, I would suggest. And then I've given you quick overview, I'm mindful of time, of some examples there, but there's lots more on our website, and I'm happy to talk you through other examples if you've got specific areas of interest in mind. And that is me.